Okay, so today we're going to look at the average velocity for an ideal gas, and we're going to use the probability density function, which in this case will be the Maxwell-Boltzmann distribution, because we are trying to come up with a formula which represents the average velocity for an ideal gas. And the Maxwell-Boltzmann distribution gives us the likelihood that for any particular v we choose on the x-axis, there will correspond a likelihood of us finding particles at those chosen velocities on the y-axis by examining the y values at those points. So to do this mathematically, we're going to have to ask the question, what is the average velocity? So that asks right there, what is the average velocity with those sharp brackets? And that's going to be equal to the integral of the velocity multiplied by the probability density function, which we will use the Maxwell-Boltzmann distribution. Now, the Maxwell-Boltzmann distribution, if you guys didn't remember it, which is just fine, that's going to be brackets m divided by 2 pi Boltzmann's constant times the temperature to the 3/2 multiplied by 2 spatial dimensions that were constant in the volume element, and e to the minus m v squared over 2 kt. All right, that looks right. So we'll go ahead and plug that in and take everything out that isn't a dV. So just rewriting this. We'll go ahead and just write everything that's not a dV. I should do it red just in case it confuses people. So the 4 pi from over here is coming out. Similarly, some of these other constants that don't have a relation to v are all coming out. All right, I think that's everything that's not a v, because we just have the first product, which will have like powers of v, I think to the power of 3, yeah. And then the e term. Okay, so I'll go ahead and do the rest in black, the actual integral. And what's left over is v cubed, e to the minus m v squared over 2 kt dV. Now, if we're going to be talking about average velocities, typically when you're asking a probability question, which is what we're doing with this p operator right over here, what this is asking is for negative infinity to a positive infinity, but because we're considering that the average velocity can only be positive in our model, we can go ahead and have these limits go from 0 to infinity. All right, so from here, yeah, it's basically just going to be some integration, and I'll go ahead and name some constants just to get rid of some fun stuff. So we'll let alpha be equal to m over 2 kt, and we'll probably just make our life just slightly easier. So we've got one alpha inside there. The m over 2 kt part, and however the pi is not part of alpha. And now we'll do the integral. We're going to have an alpha up in here in the exponent. Okay. So I guess I'll start on a fresh page for the rest of this integral. But this is just a long constant that we can call C for now, just the constant. And I'll go ahead and start on a fresh page. I think we're going to have to do some U substitutions in here for these guys. But yeah, okay, so I'll start a fresh video. Okay, so now I'm starting with the integral that we needed to finish in order to find the average velocity using the probability density function that is the Maxwell-Boltzmann distribution. It comes down to integrating this. So the trick here is some sort of clever EU substitution is definitely going to help us out, because this term right over here is the main problem. The x squared is going to be it's the issue basically, and I'm sure a lot of you who took calculus 2 have encountered the integral of e to the x squared or e to the negative x squared, and there's whole sections on just that integral. So the problem part is the v squared. So we'll let of the exponent. So we'll go ahead and get rid of the problem. So u is equal to the problem that we don't like, which would cause us to say that du would be equal to 2v and the differential element. And what we need to do is replace up here where we can. And just to illuminate things a little bit more. So this was the constant. It's kind of a long constant, but it was on part 1. So we're going to need v squareds, because that's what we've set our u to. And we'll put the extra one over here in order to match the format that we're trying to come up with for our substitutions. So even more usefully, du over 2 is equal to v dv. So now substitute where appropriate. And we're going to have a u to the minus alpha u, because that's a v squared up there that I sloppily wrote, and 1/2 du. This is now part of the constants. So we'll start from that. 1/2 times the constant times the integral of u times e minus alpha u du. Okay, so this is either integration by parts, or if you're into some of the other methods like tabular integration. I actually prefer tabular integration for this sort of situation. So we'll go ahead and do this integral. Now, remember that the original limits was minus infinity to positive infinity. So if the v squared was infinity, this one is still going to be infinity. But if this one was infinity, this would be the square root. So that's going to make our limits 0 to infinity, which is the reason why we have 0 to infinity for v average. So for tabular integration, you draw a table like this. This is going to be your derivative. This is going to be your integral columns. And then you write plus, minus, plus, minus, plus. And the product that you would like to derive, you start writing in this row and start taking derivatives, and the other product you start taking integrals. So here we'll write a u. The derivative of u is 1, followed by 0. And when you get to 0, that's what you're actually looking for, because you have this diagonal circling method. So we have e to the minus alpha u. Integrate that means bring this in the denominator. So if you were to take the derivative, e to the x dx would cancel the denominator. In this case, e to the minus au over the constant, which was a negative. And similarly down here, we're going to have a squared constant, but it will be the positive version because of the two negative ones from the other integration will cancel out. And so we diagonally circle these along with the signs. And we literally write the terms, what they're equal to. So it's going to be this one times this one. So that's a minus sign from the denominator of the minus alpha. I'll make this the equals over here. So equals minus u times e to the minus alpha u over alpha from 0 to infinity. And then this one is going to be a minus 1 times this whole one over here. From 0 to infinity. Now we have to examine these limits and see what happens. So when this one is infinity, this guy will go to 0. So this whole one is 0. When this one is 0, we can easily see that this whole term goes to 0. So for both of these terms, for both of these limits, this first term is going to be 0. Similarly, let's examine what happens when we plug in infinity. So at infinity, this whole thing will be 0 because the u is in the exponent. And at 0, anything to the power of 0 is 1. And so we have f of b minus f of a, with this being f of a, so minus, minus, and it becomes 1 over a squared. I mean alpha squared. So now we need to arrange these because this whole integral is equal to this, so we need to multiply it by the constant and by 1/2. And then also put back in for alpha. So starting on a fresh page, and I'll go ahead and write down what we had found. So we had found a constant times 1/2 times 1 over alpha squared. Now, when we put back in for these, the constant was 4 pi times something with alpha inside, but we'll go ahead and put the alpha back in, m over 2kt, multiplied by, there was a pi inside the constant, times 1/2 times 1 over alpha squared. And now we need to put alpha back inside here. I mean, yeah, replace alpha with its original m over 2kt. So it's going to be 4 pi. Oh, and this was to the power of 3 over 2. And so m over 2 pi kt to the power of 3 over 2. Then we're going to have a 4 kt squared over 2 m squared, because the 2 came from here. Alright, so now we're going to clean this up as well as we can. Alright, so we've got a 4 times a 4 over here, so that's 16. But then we have a 2 here, so that becomes an 8 now. And okay, so then we have 8 pi k squared t squared over m squared times m over 2 pi kt to the 3/2. Okay, and if we were to square both sides, we would have this situation. And so now we need to combine all of these. So we're going to get, this is 1/8. So this goes away. This is a 4. I guess I'll just write what's going on here. So we have an 8. Pi's, there's only going to be 1 in the denominator after the cancellation. K's, there will only be 1 in the numerator after the cancellation. T's, there's only going to be 1 in the numerator after the cancellation. There's going to be 1 m in the denominator after the cancellation. And let's go ahead and re-square it. I mean, you got it, depending on how you like to do your arithmetic, like you could have left it as 3/2. But so this actually is the given like the mass of the molecule in an ideal gas, this actually is the average velocity at a particular given temperature. And this should be a familiar formula to you guys from a thermodynamics textbook. All right.